Dear colleagues, I'm very glad to see you, all of you. And now we start our seminars after summer vacation. And let me introduce our today's speaker, Professor Ivan Kovalyov from University Osnabrück, Germany. And his talk is Identify Stieltjes moment problem and Jacobi matrices. Please, Ivan.
Thank you for invitation to your seminar. Today we consider indefinite Stieltjes moment problem and generalized Jacobi matrices. The first part is uh, is
Talk.
hmm?
First part of your talk.
Yes, the first part of my talk is considered a double transformation of the generalized Jacobi matrices. And first of all, recall some terms of this topic and see, and we will see some results. So let S be a sequence of real numbers, and let S Gothic S be a linear functional defined on the linear space P, and we have formula 1. So we have connection between sequence and linear functional. The next term is stone, is the main stone of our theory. So it is the set of normal indices. So it is n of s. N of s is called the set of normal indices of the sequence s, and it is defined by formula 2, where d and j is Hankel determinants. In classical case, where you consider the classical moment problem, the set of normal indices coincides with the nature numbers. So, and in the general case, we have another situation. For example, if S0 equals 0 and S1 that does not vanish, so we get the first normal indices equals 2. But in classical case, we have 1. So, and the next...
Excuse me, Ivan, what means lambda in your notation? What means lambda?
It's variable.
Arbitrary variable?
Yes, it is a complex variable.
Because your S, Gothic S, be linear function defined on linear space. At lambda yacht maybe form some span. It's not arbitrary.
Yes, but we consider linear function on the span or on the monomials.
Okay.
So, for example, 1 lambda, lambda squared, lambda cubed, and so on.
Polynomial.
Yes.
Okay, thank you.
So the next we recall what is a d n plus. So it is Hankel determinants with a shift, and in this situation we get the following condition for the set of normal indices as n. So it is a union of two sets, subsets, nu and mu, where the indices nu can be found by formula 4, and the indices mu can be found by formula 5, and indices nu and mu satisfy the following inequality 6. more than the sequence S is called regular if nu j equals to mu j for all j. And the next, so the sequence S associated with the polynomials of the first and second kind, which can be defined by the formula 7. So polynomials P are called the polynomials of the first kind, and the polynomials Q are called the polynomials of the second kind. Of course, polynomials P and Q are solution of the following system as subject to the initial condition 9. In our situation, the small p, of course, it is a monic polynomial of degree Lj. And Lj equals Nj plus 1 minus Nj, where Nj and Nj plus 1 are normal indices. More than sequence S is associated with the generalized Jacobi matrix J, and it can be defined by formula 10. So in classical case, the entrances of this matrix are constant, but in our case we have the block matrices. So the diagonal entrances are companion matrices associated with some real polynomial Pj, and another blocks you can see by the following slide. So, and the next point we have, we must define shortened matrices matrix by the following 13. So, and in this case, we obtained connection between generalized Jacobi matrix and polynomials of the first and the second kind. You can see formula 14. So, and the spectral properties and spectral object of this matrix is M function. M function of the matrix J can be found by the formula 15. More than M function have got the following condition 16 and 17, and at the moment Sk can be found by matrix J by formula 18. So, so the next step we consider Darboux transformation of generalized Jacobi matrix, and we need two matrices L and U. L and U are lower and upper triangular block matrices, which are defined by the formula 19, where the diagonal blocks can be found by the following formula. So this one and this. And now we define what is the Darboux transformation. So let J be a monic generalized Jacobi matrix, and let J admits LU factorization. We mean that J equals L times U. Then the transformation 23 is called a Darboux transformation without parameter of J, and in this situation, the new matrix JP is a generalized Jacobi matrix. And we have the first theorem. So let J be a monic Jacobi matrix. And let Pn be polynomials of the first kind associated with sequence S, and of course, and with matrix J. Then matrix J admit the LU factorization of the form if and only if the polynomials of the first kind don't vanish at 0 more than Lj Uj can be found by formula 25. And the next one, we can consider some properties of polynomials of the first kind. So if matrix J admits LU factorization, then P and J plus 1 at 0 equals the following product of UK, and we have factorization 27. And the next theorem, so let J be a monic generalized Jacobi matrix with associated with a functional S, and let J admits LU factorization, then the new matrix JP is a monic generalized Jacobi matrix. So we find the Bose transformation of matrix J. And the next, we consider some properties of this transformation. The first one, we defined linear functional lambda s by formula 28, and in this situation we get the following, that if J admits LU factorization, then the matrix JP, so we have the Darboux transformation of matrix J is JP, and the new matrix is associated with a new functional, linear functional SP, which is defined by formula 29. More than the M function transform, but by formula 30, you can see in the following slides. So, and we find a formula for polynomials of the first and the second kind. So in this situation, the new matrix JP is associated with the polynomials of first kind and second kind, and one can be found by formula 32 and 34. More than the formula 32 is called a generalized Christoffel formula. So this block is end. The next, we recall some information of the classical Stieltjes problem, and after we will consider indefinite Stieltjes moment problem. So, what is this classical Stieltjes moment problem? Given a sequence of real number, find a positive Borel measure sigma such that 35 holds. By the Hamburger-Nivenliness theorem, the Stieltjes moment problem can be reformulated in terms of the Stieltjes transform by formula 36, and in this situation we can rewrite, or we can reformulate our problem as an interpolation moment problem by formula 37. The next step, we defined generalized classes. First of all, we defined generalized linear class. So the function f meromorphic with a set of golomorphic is said to be in the generalized linear class if for every set Zj, the form 38 has at most kappa, and for some choose it has exactly kappa negative square. So in particular, if kappa equals to 0, then the class N0 coincides with Newton-Linear class. We mean the classical Newton-Linear function. More than every real polynomial, P belongs to class N kappa, and kappa and index kappa can be found by formula 39. So, of course, we can define class N kappa plus as kappa plus and class N kappa k, but today we consider indefinite Stieltjes moment problem in the class N kappa k. So its class is called generalized Stieltjes class. It consists of the function such that f belongs to the class N kappa, and that f belongs to the class N kappa, nk, yes. So, and now we defined our problem. Given L, kappa, and K, given as a sequence S of real number that describes the set M of function belongs to the class N kappa K, which have the following asymptotic expansion. So, and we have the first theorem. So, let S be a sequence of real numbers, then our problem MP kappa k is solvable if and only if the following holds. So we mean this formula. And any solution of this problem admits the representation 40a, where the parameter tau satisfies condition 32, and polynomials m and L can be found by the following formula. More than if S, we mean that the sequence S is regular, in this situation, L, J are constant. But in general case, L are polynomials. And the recurrence sequence S can be found by the following way. The next statement, so now we consider even problem, and in this situation the moment problem MP kappa k is solvable if and only if the following condition holds, and the solution can be represented by formula 45, and parameter tau satisfier 46, and entries M and L can be found by similar formula. This one. So the next statement, then the next step, we introduced generalized Stieltjes polynomials P plus and Q plus. So we consider system 47. P plus and Q plus are solution of this system subject to the initial conditionals, and these polynomials are called the generalized Stieltjes polynomials of the first and the second kind, respectively. So, and in this term, we can represented our solution of our problem. So let S be a sequence of real number, P plus and Q plus be the Stieltjes polynomials of the first and the second kind. And then any solution of our problem takes the following representation, 49, where parameter tau satisfies the following condition 50. So the next statement, the next step, we consider alpha regular sequence and alpha regular sets. So what is that? The sequence S is called alpha regular if and only if the all polynomials of the first kind does not vanish at alpha. In this situation, we can define the Stieltjes polynomial P plus and Q plus with this shift alpha by the following way. You can see in this slides, and
could you say alpha is a complex or real number?
real number.
Real number, and also I'm interested in B0, BG minus 1. What is the numbers? The given numbers?
This, you mean this?
Yes, sure.
It is an initial condition.
So from okay. And
So,
also it's real number.
Yeah. So, and okay. So, if you consider the following system 20, I'm sorry. If you consider the following system 51, of course, the solution of this system is the Stieltjes polynomials P plus and Q plus, and if we know these polynomials, we can find atoms M alpha and L alpha, which can be defined by the following way. So, and in this slides, we see some properties of Stieltjes polynomials, and it is not interesting maybe. So, and the next theorem we can see the following. Let P and Q be the sequence of the polynomial of the first and the second kind respectively. Let alpha be a real number such that polynomials of the first kind P and does not vanish at alpha. Then the generalized Christoffel formula for P takes the following form, and some similar formula for polynomials Q takes the following way. So this one, okay. And in this term, we can find another representation for Stieltjes polynomials, and we can see the formula 56 and 57. So, and we have the following theorem. So let S be alpha regular sequence. then any solution of the odd moment problem takes a representation 58, so, and parameter tau satisfies the condition 59. And indices kappa end and k end can be found by the following way. You can see this. And in the even case, we have similar representation of our solution of the form of the following form. You can see formula 60, and in this case, our parameter tau satisfies the condition which is defined by 68, and in this situation our indices kappa n and kn can be found by formula 62. Thank you.
Thank you very much, Ivan, for your interesting talk. Some questions, comments?
Okay, my first question: How we can use this blah 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 in PDE analysis?
I'm sorry.
How we can use
I understand this.
the
Where?
results in concrete PDE problem? Please explain me, please. Because this is matrix analysis. Okay, how we can use?
It is interesting questions, but if you know some papers of Crane and Langer, and it's they consider indefinite Stieltjes moment problem in class and kappa plus. So, but problem in the class and kappa k was open. Hence, it is interesting for us, and we find some solution. And for example, so this is a theorem about box transformation of Jacobi matrices. This condition is the main, because of course if 24 holds, then matrix J admits LU factorization more than its condition said that the sequence S is regular. So if the sequence S is regular, then in the representation 48 for 41, the all Li are constant. So it is concise with the classical problem. Because in classical problem we have L constants more than the physical interpretation of this problem. So we have some multipoles.
Natalie, do you understand?
Yes, sure. First, I guess that if I correctly understand, so Ivan, when you study your polynomial pair dependent on the lambda, yes. If you consider the abstract operator, also including PDE operator, we can apply functional analysis to describe the spectrum. Yes, correctly understand you in the beginning of your presentation.
Mm-hmm.
Yes, so that's why it's possible to apply for if you consider semigroup approach and study, for example, abstract Cauchy problem for some special operator, including the PD operator, so keep in mind that it's possible to study the defined spectrum or resolvence family, and we try to possible to say about the solvability certain initial boundary problem if we say about the PD. First, the second thing I understand, right?
Problem, Natalie.
Yes, if you consider the abstract Cauchy problem with a abstract operator, so for example, ut plus a is an abstract operator. Yes, to find the solution, you should describe or find the resolvence family, or for example, describe the spectrum of this A. If you describe spectrum A, you can find some information, knowledge about the behavior for big time. That's why you study some, for depending of A operators, you study some, let's say, some polynomial where instead you substitute, instead of lambda, you substitute the your operator. And why you have the representation for solution, for example. It's a functional calculus applied. You use you say, let's say you represent from integral where lambda belongs to the spectrum, and when you study under integral, you have a resolvent operator. It's in general. So it's by studying behavior of rational or irrational polynomial, like it's the first part of this presentation, P of lambda, or it's necessary to find where is the spectrum and where is the resolvent. It's the first. The second part of this presentation related with the difference equations or system difference equations. Yes, it's rising and study difference equations. Also, it's necessary to do some numeric calculations in some PDE, also including first as the second in the sum. For example, if you consider, okay, so for example, in some elliptic problems with dynamic boundary conditions, and for irregular domains, you obtain after plus Laplace and Fourier transformation, you transform this boundary problem to the difference equations. And study, of course, to find solution with difference equations, necessary some knowledge. It's as for application for PD as first. And second one, let me recall you, our seminars not only included PDE, but our contemporary analysis, which also includes the analysis talk as first. So, Roman, do you have any questions?
No.
So that's why I have some questions also, but if you know one person, some questions. Okay, Ivan, please, let's return to Formula 24. It's a beginning your... Okay, so, but could you maybe explain me what's happened if P nu zeta from 0, it tends to 0, what's problem? It's, of course, I understand that it's necessary and sufficient conditions to factorization, yes, but what's happened?
What happened? Yes. Okay. If you see, we use two matrices, matrices L and U. And in these matrices, we have some parameter. So U, L, that's all. Another coefficients we find by matrix J. So this is one. I mean, and in this situation where we consider factorization LU, we obtain the following formula 25. And in this way, we get a formula for uj. It's rational. So we have p and j plus over p and j at 0. And in this situation, we must say that p and j at 0 don't vanish for all j. So it is the first. The second step, it is the main condition because its condition is associated with solvable of the indefinite Stieltjes moment problem. Because if 24 holds, then our sequence S is regular. If sequence S is regular, then we have the all L, I in this representation are constant. In the general case, of course, it is Li are not constants because it may be polynomials, maybe constants, so we have some mix of it. But in a regular case, we have only constants. So.
Okay, thank you. But next, my question is related with your formula 32, please. Okay. What's happened if lambda tends to 0, lambda equals 0? If I understand right, lambda is any its complex.
Okay, I understand, but if this in this situation, it is if you know the classical Dabog's formula, Dabog's Christoffel formula. So 32 is generalized Christoffel formula, or sometimes it is called Dabog's Christoffel transformation of the polynomials and blah blah blah. So if we consider expression in the brackets, so it of course one can be divided by lambda. So it is not a problem because this expression simplified by lambda.
Okay, thank you. And my last question related is 47.
Sorry?
47 formula, please.
40.
Okay, so maybe some stupid
Okay, I understand. So
question, but
we
why with systems 47? Why the system is solvable? So why you said with the polynomial?
its system. So in the first time, the system is solvable because okay, we have representation 45. Yes. So this representation, so this fraction is associated with the system 47. So it we used some fact of continued fractions. So some continued fraction is associated with some difference system. And atoms M and L are generated.
So keep in mind that for any mg plus or lg plus, you obtain the similar results or not.
Sorry?
So keep in mind for any mg plus and lg I plus 1. So it's possible to construct solvability 47, solution 47 with generalized Stieltjes polynomial. Yes or no? So,
No, it is correct.
okay. Thank you.
For arbitrary M and L?
No, it is not arbitrary.
No, Natalie
M.
asked you for
I
any.
understand. So we have representation 45. In this representation, we get M and L. Yes.
Yeah.
Okay. M and L can be found by formula 43 and 44, and these items generated system 47.
What do you know about regularity, this function?
We didn't consider it.
You specify for explicit representation, yes, for which function? Or you say that which function is generated by f of z, yes? Or no? No, I keep in mind mg plus 1, lg plus 1 is generated with function f, yes?
Yes.
Yes, sure. And that's why you, as for function f, you assume with representative reflection.
Mm-hmm.
But what is asymptotic behavior a function f if z tends to?
Okay, we have this asymptotic behavior, but L is 2nj minus 2 or 2nj plus minus 1. So if we can consider even case or odd case.
But as for me, if z tends to 0, it's constant, yes or no?
No,
Sorry?
no, it's a real number.
No, so yes, it's about real number. Yes, it's
Of course.
no.
Because this is expansion, Natalie.
Yeah, sure, yes, I understand. But it's the expansion for t is the expansion for large z. But z here is only real number, yes, not its complex number.
Yeah, of course.
Why, of course.
No, because asymptotic expansion in Laurent series. Of course,
Yes, I
here
understand.
for your
But
problem,
it's possible to
all the
consider,
real.
okay, Roman, I understand it, but it's possible to consider if function f depends on the complex number z. No, so the complex parameter z.
No, okay, of course, that is complex.
Yeah.
Yeah, that complex. Natalia asked about
Yes, sure.
S small. Possible a small complex or not?
What?
Ah.
Okay, so thank you. Some questions, comments, and
So, my wishes. First of
okay,
all,
Roman.
if you speak about such type problems, more better start from explanation how appear this problem, because we are not specialists.
Yeah, I understand, but it is
That's not clear. What
it is
happened?
good remarks, but other hand, it is hard questions.
And now my understanding is next. If you consider some PD, okay, if you construct some symbolic polynomial, and after then you analyze characteristic number, you can use your result. This is my understanding.
Yes.
But about Natalie question, what happened when polynomial equals 0 is clear. It means you have problem. No, one of the characteristic number is equal 0. For this reason, you have some problem with solvability, of course. Natalie, understand?
Okay, I understand it.
For this reason, my opinion, Ivan consider good situation when we have no problem with symbolic form. So this is simple roots, for example. Here is impossible multiple roots. Okay. Thank you, Ivan. I understand your logic.
So, some questions, comments, colleagues? No. So, thank you very much again. I know, like this. Ivan, thank you very much. And we finish our today's seminars.